Hello everyone. Today we're going to be going over Newton's laws problems. The two main aspects of Newton's laws that we're going to be discussing is the fact that force is equal to mass times acceleration, and an object in motion will stay in motion unless acted on by another force. So we're going to be going over two problems here. Mass with force at an angle, just basically just a block, and they tell you that the force is acting on the block at some angle, like it's being pulled basically, and the angle is from the horizontal, and mass attached to a free hanging mass. So this mass here is attached to a free hanging mass over the edge, and they give you the coefficients of friction. So let's get started. So our first problem is mass with force at an angle. So here we have our mass. It's given to us in the problem that is 20.14 kilograms. And they tell us that the force is acting on the object at 30 newtons at 18.4 degrees above the horizontal. And they ask, what is the speed of the box after 4.5 seconds? So right here you can see that we have our kinematic equations. And a lot of times with these problems, it's important to look at what we know and break it down into more simpler pieces of information, and then see how it can apply to these four kinematic equations. So the first step when it comes to this problem is you always redraw the problem with your own take on it, basically. I think that redrawing the problem makes sure that you understand what's going on, and with any of these force problems, you should be writing out your work. So this is a good place to get started. Another thing that is really important to do is write out everything that you know. So we know that the mass is 20.14 kilograms. We know that the gravitational acceleration is 9.81 meters per second squared. And we know that the force is acting on it at an angle. And we must find the component vectors. Also, what you should draw is any vectors that are acting on the object. Every object that's sitting on like a table or an unmoving mass is going to have a force normal and a force due to gravity, which is mass times acceleration, or mass times the gravitational acceleration constant. Over here, though, you see that I take the force vector, and I'm basically going to create a triangle out of it. Every vector, if it's not perfectly perpendicular or parallel, like if it's not perfectly sitting on the x or y axis, it's going to be made of two component vectors, which, if added together, will make this vector at the angle. So it's basically made out of an x vector added to a y vector, which makes this total vector with the hypotenuse of 30.0 newtons at this angle. So basically what we're going to do next is we're just going to start filling in more pieces of information. We can solve for force due to gravity. We can solve for x and y of this triangle using trigonometry. We're just going to move on from there. So as you can see here, if you take cosine theta equals adjacent over hypotenuse, and we solve for x, we get 30 cosine times the angle, or of the angle I meant to say, and we get our x component vector is 28.47 newtons. We can do the same thing for the y component vector. Sine theta is equal to opposite over hypotenuse. Solve for y. 30 sine of 18.4 degrees. We get 9.47 newtons. So now we have our horizontal force and our vertical force. Now, it's also important to reconsider what the question was asking for, which, if I go back here for a second, what is the speed of the box after 4.5 seconds? So it's good for you to start thinking about how are we going to solve for speed. Well, you're going to need to know the force acting on the box, so that you can figure out how fast it's going after the 4.5 seconds that force is acting on the box. So as you can see here, really all we care about is going to be the horizontal force and the horizontal acceleration. The vertical the box isn't going to lift off the ground from this force, basically. If we look at our force due to gravity, you do a quick calculation or do it in your calculator, you can see that this force here down 20 times 10, basically, it's going to be around 200, is much larger than this force up from this vector. And so we know that it's not going to lift off the ground. We don't need to worry about that acceleration. So then we have our horizontal acceleration. So we have the force, which is 20.47 newtons, is equal to our mass times our acceleration. We solve for acceleration, 1.14 meters per second squared. And then we look at our kinematic equations, and we want to solve for velocity. This is the kinematic equation I chose. A lot of times with kinematic equations, you can pick more than one to solve the problem. So velocity is equal to, the box starts from rest, and so we have 0 plus 1.41, which is our acceleration, times time. It was saying after 4.5 seconds of the box moving, and we get velocity is equal to 6.36 meters per second. Now another way to do this is, if you know units, you know that velocity is meters per second, as seen here. We know that acceleration is meters per second squared. And this value right here is 4.5 seconds. So 4.5 seconds is on the top. One of the seconds on the bottom is going to cancel out, and we're left with the units of meters per second, which is what we want in our answer. So the point of me telling you that was sometimes it's possible to solve these without using a kinematic equation, but the kinematic equations almost always work. And it's a constant way that you can always solve the problem, basically. So this is something that I included also for this problem. In case if you ever get a question like this and they ask for force normal, this is how they would go about solving it, or how you would go about solving it. So we have our box, we have force normal, we have force due to gravity. Now what we know about the component vectors is that the up vector is 9.47 newtons. Now we know that force normal must always be equal and opposite to the force due to gravity so that this object is staying still, essentially. Now what we do here is we find that the force due to gravity is 20.14 kilograms times 9.81 meters per second squared. This is our force due to gravity. The up force must be equal to the down force in order for the box to not move. We know that it'll sit at rest. So we have force normal plus this, plus the up force, must be equal to this. So basically our total up force must be equal to our total downward force. So we have force normal, a vector pointing up. We have this from the component vector from our 30 newtons. This is another up vector. We add those two together and it must be equal to all the down vectors, which here we have force due to gravity, and we find that force normal is equal to 188.1 newtons. So moving on to our next question, mass attached to a free hanging mass. So it's this mass attached by a string over this pulley type thing, or like a wheel, to this mass hanging here. And we're given these two coefficients of friction. This is static friction, so when the box is not moving yet, and the coefficient due to, or the kinetic friction, which is once the object is in motion. This is the new force friction. So we get two questions right here. What is the acceleration when the 14 kilogram box moves to the left? What is the acceleration when the 14 kilogram box moves to the right? Once again, we have our kinematic equations, which are going to help us to solve this problem. All right, so here I basically just included all the work from the start, and I'm just going to walk you through this. So here we have our force diagram and all of the vectors that are acting on, all the vectors, or you can call them forces, that are acting on each of these boxes. So for the first problem, the box is moving to the left, and that means that it would be deaccelerating, right? If this box is moving to the left and it's being pulled down by this box, it's probably slowing down. I don't know if you can picture that in your head, but try to. Then we have always force normal and force due to gravity, because this box is sitting on a surface. And then these forces that are acting to the right, we have force tension due to the rope. We have force friction, which is always opposite to the way that the box is moving. So if it's moving to the left, the force friction is going to be to the right since it's slowing it down. In this box, we only have two forces, force tension moving up and force due to gravity moving down. We don't have force normal because it's not sitting on a surface. We have our coefficients of friction here, and I was starting to write out some knowns. We are going to know the force due to gravity on this box, box 1. We're going to know the force due to gravity for this box, box 2. We're also going to know the force normal since it's equal and opposite to that. So if the box is moving to the left, here we go. We know that the vertical force must be 0, right? So force gravity minus force normal must be equal to 0. We know that they must be equal to each other. That's pretty straightforward. Now let's talk about our horizontal force. Now our total force is always force equal to mass times acceleration. Now the forces included here are going to be force tension and force friction. And force friction is always equal to the coefficient of friction times the force normal. So our force total must be equal to force tension minus force friction. Now for total force, we can substitute in mass times acceleration, and we get this equation here. We also substituted in this for force friction. We have our coefficient of friction times, and then this is what force normal is, since force normal is equal to mg. And then we're going to solve these equations for t. This is just something that you have to know how to do for this problem, but if we solve the equations for t, that's like basically the commonality that these two boxes have. The force tension for this box is going to be equal to the force tension for this box. And you'll see later on the calculations, the way you can solve this problem is you set the force tensions equal to each other after you've solved for them, and that allows you to really figure out what you need to know. So then we have our vertical force, we have force tension, and force due to gravity, mass times gravitational acceleration. Our total force is equal to tension minus mg. We know that the tension is greater than the gravitational force because the box is going to move up. Because this box is moving to the left, it's pulling this up. We know that force tension has to be greater than force gravity. We can substitute in for force, mass times acceleration, since that's always overall force. Mass times acceleration is equal to tension minus force due to gravity. We're going to solve this for t. We get t is equal to this right here. And it's really important also while you're solving these to write in which one's mass 1 and mass 2, because that's really easy to get confused. So mass 1 is in mass for this box 1, mass 2 for this box, mass 2. So now what we're going to do, we're going to set the tensions equal to one another and solve for the acceleration. So we have this tension from right here, and we have this tension from up here. And this is really easy to make a sign error, so it's important that you go through this slowly. And then we're basically going to factor things out and try and combine like terms. So we get acceleration. You can factor out an a from both of these two terms. We can factor out gravity from both of these two terms. Remember, what we really want is the acceleration in this problem. That's what they're asking for. I'll go back a slide. What is the acceleration when the 14 kilogram box moves to the left? What is the acceleration when the 14 kilogram box moves to the right? So right here, I did this problem for moving to the left. If you solve for acceleration, you get this equation here, and if you plug in all the numbers, you'll get the answer. Now, I'm going to leave that second question up to all of you to answer as some practice, but it's going to be this exact same concept. You're going to want to go through, you're going to want to find the horizontal and vertical forces for each box. I mean, as you know, this one has horizontal and vertical. This one only has vertical forces. You're going to solve for force tension, set it equal to each other. Just a couple things are going to be different. It'll be some good practice for you. So I hope that helps everybody. And that is our video on example problems of Newton's laws. Thank you.